Welcome, ladies and gentlemen. So, we are going to talk about the topic of biochemistry this unit, and we're really going to kind of breeze through a lot of the concepts. This is stuff that you should have covered in pretty consistent detail as underclassmen, both in your previous biology course as well as chemistry. So the idea here really is to just kind of give you a refresher, because a lot of these concepts are going to come back as we continue talking about things this year. So let's kind of dive into chapter 2, which really is just a big, quick overview of some basic chemical topics. So, first and foremost, we're talking about matter, right? So, matter is anything that takes up space and has mass. And so, what we're talking about here are elements and compounds. So, just remember that an element is a substance that can't be broken down into any other substance by chemical reactions. So, there's no physical means, chemical means of breaking elements down into any other substances, at least into substances that still retain the properties of that element. Are there things that are smaller than an element? Yes, of course. But we start breaking them down into those constituent pieces and they start losing the properties of that element. A compound, on the other hand, is a substance containing two or more elements in some sort of fixed ratio. And a compound can be broken down into those individual elements, but once again, will lose the characteristics of that compound because very often we see that those compounds have very unique sets of characteristics that are often very different from the elements that make them up. For example, water is made up of hydrogen and an oxygen. Take the two properties of hydrogen and oxygen as individual elements. They're both gases, they're both relatively flammable, and yet we combine them into that fixed ratio of two hydrogens to one oxygen to make compounds, to make the compound of water. And now we can look at it as a liquid typically. We put it out, use it to put out those fires. So definitely different compositions of those elements present their own unique set of characteristics. And as organisms, we're made of matter. We are matter. We do have space. We do have mass. And we are made up of a combination of these elements and compounds. And that is what drives the way that we are structured and the way that we function. So speaking of life, about 20 to 25% of the 92 naturally occurring elements are essential to living things. That being said, four of them make up 96% of living matter, and that's your carbon, your hydrogen, your oxygen, and your nitrogen. The other 4% that are there are your trace elements. And so these are elements that are required in minute quantities. That being said, just because they're required in small proportions to your body mass doesn't mean that they aren't essential in the way that your body functions. So, an example, iodine is only needed in a very small amount, less than a milligram a day, and yet lack of that iodine for significant portions of time, and you form these things called goiters, which are these sort of growths on your thyroid gland. Well, it is your thyroid gland swelling. So sort of think of somebody who's got an Adam's apple, but then make it bigger, and it will grow over time. It's your thyroid gland actually swelling up because it isn't capable of producing the thyroid hormones that it is supposed to make because an essential part of those thyroid hormones chemical composition is this iodine. So we often get that iodine in our diet in the form of salt. We iodinize your salt. Go check out the labels on salt containers, and you can buy iodinized salt and non-iodinized salt. And we do this as a really easy means of getting that iodine into people's diets to ensure that that goiter doesn't form. It's not necessarily life-threatening, it just doesn't look particularly normal, and can be uncomfortable. Start adding the iodine back to their diet, and that goiter can actually shrink, at least to some degree, depending on how big it started off in the first place. So let's talk atomic structure here for a moment and just refresh our brains on what we're dealing with. So remember that an atom is the smallest unit of matter that still retains the properties of the element that it makes up. So we focus mostly on atomic structure from the three biggest subatomic particles. Those are your protons, your neutrons, and your electrons, right? So your neutrons are of a neutral charge, your protons are positive. Those guys reside in the nucleus. As a result, the nucleus has an overall positive charge from those protons. And then your electrons are the negatively charged particles that are floating outside of that nucleus. That positive charge on that nucleus is what's holding those negative electrons to it, right? Opposites attract. Um, when we look at your periodic table, right, your atomic number is the number of protons, and that is ultimately the ordering of the elements in that table. Your mass number is the sum of the protons and the neutrons, right? So it's the overall mass of your nucleus. We look at the periodic table, and it's most tables, I should say, report that not as a mass number, but instead an atomic mass. Um, and so it's kind of your mass number in the sense that it is the mass of the nuclei of those atoms, but if you look, a mass number should be a solid full number, right? 1, 2, 3, that sort of thing. Your atomic mass, though, if you look at your periodic table, usually is some big long decimal. And the reason for that is because that atomic mass takes into consideration the quantities, the weighted quantities of isotopes that exist for that element. So isotopes are an atom of an element that differs in the number of neutrons. So keep this in the back of your head. If I change the number of protons, I change the element. If I change the number of neutrons in an atom, then I'm creating an isotope. And adding or subtracting those neutrons ultimately changes the mass of that element because I'm changing the number of particles in the nuclei, and that's where the bulk of the mass of an atom comes from. Um, so when we look at changing these number of neutrons, making them heavier or lighter than sort of the average element, that's where that atomic mass is coming from. So if I look at the mass number is just the protons and the neutrons within a particular atom. The mass number that we see reported on most periodic tables isn't the mass number, it's actually the atomic number. And that atomic number is a weighted average of all of the different isotopes that exist for a particular element in nature. So if I look at something like carbon, it's not a mass number of 6 that's reported. Instead, it's a decimal form of that because I'm taking into consideration how much carbon-12 exists, how much carbon-14 exists, carbon-13 exists in nature, and then weighting that average. So if I find carbon-12 occurs 50% of the time, then it gets 50% of that average. If carbon-13 exists in 30% of the environment, then it gets a 30% weight. So that's kind of where that number is coming from. If you round it, you get a close approximation to the mass number of a typical atom of that particular element. So isotopes are interesting because you get the heavier and heavier they become, the more likely they are to be radioactive isotopes. And radioactive isotopes spontaneously decay, where they'll give off particles and energy and break down into other elements as a result. So we mentioned radioactive isotopes when we talked about dating fossils, right? We can use certain elements and that consistent half-life as a way to understand how old a particular object is based on the proportions of isotopes that it currently has compared to what it would have had when it was first formed. We also use them a lot in medical practices. So we can use them as trace elements for metabolic processes. How quickly does your body break certain um, isotopes down makes a difference in terms of not only just following is your body doing that process properly? But it also becomes an interesting portion of discussion when we talk about giving you certain pharmaceuticals, and making sure that they're breaking down at a rate that we want them to, not too fast, not too slow, so that you actually get the benefit of that drug. We also use them in diagnosing medical disorders. So in a lot of things like PET scans, CAT scans, MRIs, they may use radioactive isotopes as a way to highlight certain features to be able to see some more of that soft tissue that might be more difficult without having that extra dye, if you will, extra way to identify certain things.